Hey, what's up?
So while doing the assignment, I had a question.
Okay.
The C problem, and you tell us to change the mesh size and ask, and we have to find the elements, right?
Yep.
I'm getting the elements like this.
Okay. Yep. That's fine.
But over here it says notice that how 2.5 is half the original element size, 10 mm is double than the original. But
Yep.
Yeah.
Yeah, no, that's right.
That's right.
Think about it. So when you define the element size, defining this length, right? So let's pretend we have a square that's length 1, right? What happens if we make a square where each length is 2? Area of this one is 1, right? Area of this one, it's not 2, it's 4, right?
Yeah.
So when you go kind of half the size, you don't get half and you don't get double the number of elements. You actually get closer to 4x, actually, because it's a 2D system. And so that effect is actually being magnified even more when you put 3D. Because think of a cube, right? The cube, volume of a cube, right? All the sides are 1, just 1. But if this is 2, the volume would be 8. And so that effect actually gets magnified. So actually, what we did, where you cut the element size in half, that's actually a pretty extreme change in the problem size. For 2D, you're only going about, it's not exactly 4x because there's other shape factors, so it ends up being closer like half times. But for 3D, it's going to be 6 to 7 times. Yeah, that's exactly it. Mhm.
You're right. I knew you looked familiar. Dear God. That's funny.
Not today. No, today we're just taking notes. Mhm.
See part of probably with the machine, changing the value of the machine with that.
It's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. Hopefully everyone had a good weekend. Right? It's kind of a funny moment last class for those of you joining. So I kind of made a joke about my wife in last class, and then I started coughing like crazy because I swallowed some spit. So lesson learned: wife is always right. Don't make fun of the wife, otherwise bad stuff will happen. Okay, so we're not going to make fun of my wife today. She's awesome. I love her. She brightens up my world, and so all of it. So please don't kill me. Okay. So today's lecture. So last time we met, last Wednesday, we had our first ANSYS activity. So I know it was a little hectic. It always kind of is, just because it's our first time using ANSYS. And so today we're going to take a little bit of a step back. Today is just going to be just a lecture day. And so what I want to talk about today is just a little bit of theory behind FEA. Not that much. And so today we're going to go over just a little bit of the history behind FEA, kind of what FEA actually means. And so because I think people just have kind of wildly different in interpretation of what finite element analysis is. Just to kind of set the stage. So this course, just kind of by its design, is application focused, and so we'll be doing a lot of ANSYS in the class. But I still think it's important just to know just a little bit about the background of FEA, kind of where it's coming from, what it aims to do, just because I think it gives you kind of a better understanding of actually using the software. Okay, and so today will be kind of basically the only day we'll be doing this, and so I kind of want to cover it just so you kind of know, because I think FEA has a little bit of an interesting history that I think not that many people really know about. All right, and so that's it for my announcements. Remember, activity 1's due Friday, and so make sure you guys are working on that. If you have questions on it, definitely feel free to shoot me an email or come to office hours, and I'd be happy to help. All right, any questions before we get started for today?
I have one, Dr. Chan.
Sure.
I can go after anyone has any questions.
No, you're the only one.
Okay. My first question is, I reviewed this course syllabus, and I'm sure you mentioned this in the first day of class, but we're scheduled to do 8 assignments this semester.
Correct.
Does that imply that we're going to have assignments every 2 weeks, every other week?
Yes, okay. Yes. So that is the plan. So every other week we're going to have an ANSYS activity, and so it'll be basically on all the odd number of weeks. So weeks 1, 3, 5, 7, 9, 11.
Sounds good.
I think we might skip one in between because I think there's the midterm project in between there. But yeah, every other week we'll be learning something new about ANSYS. Yeah.
Sounds good. This question may be I may be getting too ahead, but one question I have regarding to FEA that recently popped up in my head is I'd like to know the difference between what von Mises stresses and what principal stresses are. I'm thinking they're calculated the same in the software. Again, I know I'm getting ahead of myself, but that's a question I'd love to know, the difference between von Mises stresses and principal stresses in FEA.
Yeah. I mean, we'll definitely get there. That's not something we're going to cover today, but we'll definitely talk about it later. That is definitely a fair question because I had you calculate both. And it looked the same, right? And so from the activity, it looked like both had the same kind of values.
Common sense is telling me the math is different, which I'm pretty sure it is, but I'm interested in the concept. Like, why does the engineer need to know, why would the engineer want to know the von Mises stress rather than the principal stresses and vice versa?
Yeah, we'll get to all of that for sure. And so, it is a little bit early, but yeah, we'll definitely be talking about that.
Sounds good.
All right. Yeah. Question.
Just had a question about
okay.
In terms of layout, how is there a specific way you want us to add certain?
As long as it's neat and the screenshots are legible and the responses are in complete sentences, then that's fine. Yeah. I've had a wide range of people going hardcore and doing it in LaTeX and then really making format nicely. Obviously, that's really nice. It makes grading easy. But I've also had people turn in like a 50-page document for every activity, where each page was a different screenshot. I mean, you can do that. I would prefer not, but I won't grade you down on it because the way I see the activities is that the activities are learning experiences, and so each time we're doing something new, and so I want you to focus more on what's something new about ANSYS that I'm learning, and don't worry too much about what you're training. As long as I see everything's complete and I can see it all there, then that's good enough for me. So the parts that I'm really going to grade are going to be the midterm project and the final project. That I'm going to be more strict about the formats. Yeah. All right, so let's go and get started. So the theme for today is going to be just theory behind FEA. Okay. And so in reality, there's actually a lot of theory behind FEA. And I know some of you guys are coming from my 541 class that happened, I think, a year and a half ago. And so in that class, you got a big dose of theory behind FEA because that's what the whole class is about. It's about the theory behind FEA. But today I just wanted to do just kind of a brief introduction, just so that you kind of have a little bit of knowledge of the history, what FEA actually is, and so what it actually means, just to kind of give a bit more context to what we learn in the application. Okay. And so first, what is FEA? So FEA, of course, stands for the finite element analysis. Okay. And so a lot of people, when they think of FEA nowadays, they think of the softwares. And so they think of like ANSYS. Another software that's out there is Abacus, maybe SolidWorks simulation. Okay. But at its core, actually, finite elements has nothing to do with any of that. So ANSYS, finite elements doesn't have anything to do with compute. It doesn't even have anything to do with computers. Okay. So at its core, FEA is actually a technique for transforming differential equations into a system of algebraic equations. So for example, let's say we have a differential equation like this. Okay. I'm going to use the heat equation as an example, just because it's one of the only equations that I've memorized. So a lot of engineering, a lot of applied math, a lot of science, are governed by equations that look like this. And so the relationships between basically the derivatives of a certain quantity. Okay. And so, for example, here we have the heat equation. So where big T here is the temperature. And so this equation basically states the relationship between the time derivative and the space derivative and the second space derivative of the temperature within a solid. Okay. And so what FEA does, then it takes a differential equation like this, and it turns it into a system of linear equations. Okay, and so by linear equations, I basically mean algebra. And so algebra, you can represent in a lot of different ways, but most commonly, especially for a very large system like this, you'll see your system of algebraic equations expressed in what's called matrix form. It might look something like this. And so you might be familiar with the expression AX is equal to B. Okay. Where A here, that's known as our coefficient matrix, X is our solution vector, and B is our right-hand side vector. Okay. Where if you kind of think back to your linear algebra class when you were in undergrad, You know, the matrix A, if you have just a very modest system of like maybe 4 equations and 4 unknowns, then A would be 4 rows, 4 columns. X would have 4 entries. B would have 4 entries as well. Okay. Right. So that's what FEA was designed to do. Okay. The problem with FEA at the time, so when it was first being developed, is that, okay, you know, what scientists basically said was that we have a differential equation. This is a really hard math problem. Differential equations are by no means trivial to solve. You know, they're always involved in some kind of tricks to some degree. Okay. And so, you know, the person that developed FEA was like, okay, we have this really hard math problem. If we go through this process of FEA, which is by no means an easy process, FEA is still a pretty hard process. Say difficult, not hard. Okay. We end up with a system of linear equations. So you might think like, oh, you know, that makes the problem easier. No, it doesn't, because, you know, the system of linear equations that you actually get from this is something that's just not very practical. And so if you have a system of equations that's maybe 4 equations, 4 unknowns, like, okay, you know, you can solve that. That's not too bad. But with FEA, you end up with a system that is probably closer to like, you know, maybe 10,000 equations by 10,000 unknowns. Okay. And so good luck solving that. And so that is not a system that's easy to solve. And so when FEA was kind of first proposed, it was first kind of published in the literature, it basically looked, the way people viewed it was like this. So you start with a really hard math problem. You go through this very difficult, very complicated, complex process known as finite element analysis. And what you get from it is just another really hard math problem, just in a different form. And so what basically people said was that, you know, this is bullshit. Like, why should we go through this FEA process if we're not going to get anything from it? It's just, you're just doing math just for fun. Okay. And so it actually took a very long time for FEA to become, you know, actually used in practice. Okay.
I have a question, Dr. Chan,
Uh-huh.
and your last sentence gets to it. Do you know around what years FEA became popular in the commercial industry?
I want to say it really started being used, or people really started to use it more, like basically when computers started coming around. So you're talking
around
like
the early
70s,
okay.
70s, 80s is when it really started to kind of pick up steam. Yeah.
Sounds good.
Mm-hmm. Yeah, and so with that, you know, the reason FEA started to catch on was that, you know, we have this really hard math problem down here, but the difference here is that this really hard math problem is an algebra problem at its core. Okay? It's a very long and very not practical algebra problem, but it's still algebra. Okay? What people were starting to discover kind of in the 70s and 80s, as computers kind of started to become more and more powerful, was that computers are really, really good at doing algebra. Because the way that a lot of algebra algorithms were designed, it fit really well with the way a lot of computers were built from like a hardware perspective, okay? And so a lot of the calculations that you do kind of line up really nicely in terms of, you know, lining up the RAM and, you know, and all that stuff, okay? And so as people start to discover that, you know, computers are good at algebra, then people start thinking, you know, if we can turn basically any kind of problem or any kind of problem that we have into algebra, then computers are going to be a good way to solve it. And so that's when FEA as an engineering tool really started to take off. Okay. And this notion that computers are basically turning any kind of problem into an algebra problem is still, I think, being developed today. So I think if you kind of read any of the tech news, there's a lot of discussion now about AI, artificial intelligence, and machine learning. Okay. And if you look at machine learning, it's really nothing more the same as this. And so basically you're taking basically, human processes and turning them into a gigantic algebra problem. Okay. And so I think machine learning, it has roots in image recognition. And so, basically what it does is that, you feed it an image. And what you do is you digitize the image, you run it through a gigantic algebra problem, and the computer can tell you whether it's a cat or not. Okay. And so I think, we're still kind of finding applications for this even today. And so FEA is kind of one of the early ones to do this. Okay. So all that's good. And so right now, what we have is that FEA, it's good because it can take these differential equations, turn it into an algebra problem, and the algebra problem can be solved with the computer. Okay. And so how does this help engineering? Okay. And so when you're doing engineering analysis, a lot of times you're interested in predicting what is the physical response of the system, okay? And that usually involves solving differential equations. And so what people start to know is that most physical systems have their behavior governed by differential equations. Okay, and so just by just the first example that we did today. So for heat transfer, right? So for thermal situations, all the thermal behavior follows the heat equation. Okay? And you can come up with the same equations for like fluid mechanics, for structural mechanics, electromagnetism. Applied science is full of these differential equations. Okay. And so now kind of the idea of using FEA for engineering analysis started to take place because, we have, as engineers, you have these kind of physical systems that are governed by differential equations, okay? Most of the times these differential equations are really difficult, if not impossible to solve by hand, okay? But if we use FEA, then we can use computers to solve them, and then we can use the computer results to kind of augment our engineering analysis. And so kind of the thought process kind of started like this, okay? And so I'm going to make a flow chart of kind of how FEA kind of got to the point where it is today. Okay. So you start with a physical engineering system. So, this could be like an airplane wing, it could be like a car engine, it could be a bridge that you're designing, some electrical component, whatever. Okay. So as an engineer, you need to do some kind of analysis on this, to help with your design work, or maybe you're doing, failure analysis, something like that. Okay. So you start with a physical engineering system that you want to learn more about. All right, so that physical engineering system has its own governing differential equations. Okay, whether it be a structural system, thermal system, fluid system, electromagnetic system, there's always going to be some differential equations that's governed by it. Okay, and so ideally, if you're able to solve those differential equations, you're going to understand a lot about your system. So you can do a lot of predictive modeling. Okay, the difficult thing is that for practical systems where you have complex geometries, complex conditions, this is very difficult, if not impossible to do, okay? And so we need some help in order for us to solve these equations. So that's where FEA comes in, okay? FEA. And so through FEA, we can take those governing differential equations and turn them into a system of algebraic equations. And the good thing about the FEA at this point, kind of where we are in FEA technology, is that those algorithms, that technique of FEA is has been coded many times. So it's kind of built into a lot of the softwares like ANSYS and SolidWorks simulation. Okay. Then once you kind of arrive at this point, when you have a system of algebraic equations, you need to solve it. And so at this point, this is when you really leverage the power of computers. Okay? And so computers, what you do is you solve. And so the computer kind of goes through, it kind of does its thing. It computes the solution for you, okay, using its computer algorithms. At this point, the solution is actually not really in a useful form because it's kind of just a bunch of numbers in the computer. And so another thing that the software does, especially nice softwares like ANSYS, is that it helps kind of process the information for you. So I call this post-processing. And through post-processing, it basically takes those results and presents it in a way that's useful. So you get things like the deformation field, like the stress field that we saw on last Wednesday. Okay. From that engineering results of interest. So that's kind of basically where we stopped. So at the end of activity one, we kind of stopped kind of right here. Okay. And so I basically had you get those results and then just present them. Okay. But in reality, you would take those results and you do some kind of additional work on them. So you use the results to either help you design a part or maybe to do some failure analysis, what have you. Okay. And so this is kind of where engineering work kind of resumes from here. Okay, so I call this engineering design and analysis. All right, so that's kind of that's kind of how we arrived here. Okay, and so that's kind of how FEA kind of started as it started not even in engineering, it started in the applied math field. People kind of ignored it for a long time, but then when computers kind of came into being and people started to use it, then that's kind of where we are today. Okay. The nice thing too is that these finite element softwares like ANSYS are developed by by great companies like like ANSYS, and so a lot of this actually is handled, I call it underneath the hood, because it's there's very little that you realize is happening, but there's actually quite a lot of stuff that's kind of happening underneath the hood. Any questions on this so far? All right. And so what does this mean for for broader analysis? And so this tells us that FEA, we're not just limited to just kind of physical systems, and we're not really just limited to what ANSYS allows us to do. In theory, you can apply FEA to any system that's governed by a differential equation. So this is really nice because, you know, every kind of where the cutting edge of, you know, one of the cutting edges of research nowadays is if you're studying things like structural mechanics, thermal, fluid analysis, that a lot of people are coming up with kind of twists and additions to the governing equation. So they may have a Navier-Stokes, but they may have like an extra term to account for turbulence, something like that. Or you might have the heat equation with like an extra couple terms to account for, you know, radiation heat transfer. Okay. And so, you know, the good thing about FEA is that, you know, when the equations do change, or when people come up with kind of breakthroughs in the equations, you can always modify the FEA to basically solve those equations. So FEA is actually very flexible. So as long as there's a differential equation, you can solve it with FEA. And FEA is actually used in a lot of surprising applications as well. So, you know, a lot of times when you think of differential equations, you think of kind of physical systems, but there's a lot of weird, you know, mostly in the realm of like, you know, physicists and like theoretical math, where they come up with just weird equations because, I don't know, I guess that's just what they do with their time. And so, you know, if they can't solve it by hand, then, you know, they might solve it with FEA or something like that. And so, you know, FEA, you know, people mostly associate it as an engineering tool, but, you know, at its core, it's mostly just a math tool.
Dr. Chan.
Yeah.
You mentioned all the scenarios where FEA can be used. Can you provide some scenarios where it might not be used, if you have any memory?
Yeah. Basically, in situations where you know, where you don't have a differential equation, and so, you know, there's a lot of analysis that goes into like economic analysis in terms of, you know, whether your whether your product's gonna be profitable or not. FEA, no matter how sophisticated it's going to be, it's never going to replace physical testing as well. And so you can do, you know, the most sophisticated analysis you can do in the computer, you know, and it could all be good, but, you know, no one's going to build your product, or no one's going to, you know, actually use it until you actually have physical testing.
Are there any systems out there that can be governed by a differential equation, or all systems can be governed by a differential equation?
That's a good question.
Yeah, I mean, that's what I'm thinking. I'm thinking about like any exceptions where a governing equation doesn't apply to a certain system, but that might be out of my realm, and I don't want to waste any class time. So
no, it's a good question. You know, most of the ones that are in mechanical engineering have some kind of differential equation associated with it. I think where things get really difficult are when you have
like space or something.
No, space has a
Space. Okay.
I think where you start to kind of get away from is when you do a lot of engineering work that relies on empirical data. And so like kind of the cutting edge kind of material science. And so when you're doing things like you're measuring like the stiffness and the Young's modulus for materials and getting theory about that. Last time I checked, I think a lot of that is not, they haven't really come up with good differential models for it, because a lot of that is just purely observational. So
I see.
You have a new material, so they do a test on it, so they come up with, you know, its stiffness, and there's really not a way to kind of model that with a differential equation.
Do you have any familiarity with FEA and being used for composite materials?
No, it's a good question. I think people have tried. I think there's people out there trying to come up with good material models that are differential equations, but I think it's still kind of, you know, not really at a spot where it's reliable yet. And so
I see.
That's the last I kind of checked on it. You know, that was kind of a while. So maybe it's gotten better now. Okay. All right, so let's get to kind of more useful stuff so that was kind of a nice you know, history lesson. I think is useful. But let's get into the theory that's you know, that's actually going to be useful when you're actually using ANSYS. Okay? And so the first concept that we'll go over is this concept of a boundary value problem. Okay? Let's define that. So a boundary value problem, you know, one way that you can define it is that it's a mathematical expression for a basically the type of problems that finite elements is designed to solve. So it's basically a mathematical expression for basically a physical situation that you want to model. Okay. And so a lot of the FEA theory, and if you take 541, you'll see a lot of this. Basically, whenever you come up with a new FEA problem or FEA analysis, you first have to define its boundary value problem. So the boundary value problem is kind of the first step before you actually create a finite element solution for a problem. Okay. And so there's three parts to a boundary value problem, and we'll go over each one and why they're important. And so the first is the domain. Next is the governing equations. Three are the boundary conditions. All right, so the reason I'm kind of bringing this up and why this is useful is that, when you're doing an ANSYS analysis, when you're doing any kind of FEA, it's always useful to think about, what is the corresponding boundary value problem? Because it kind of helps to, it helps to, first of all, it mostly just helps to kind of stay organized in terms of, what is your domain, what are the equations you're solving, what are the boundary conditions. But it's also kind of useful to think about in terms of, debugging stuff later. Okay, so let's go through each one and define, why it's important. Let's start with the domain. Okay, so the domain basically specifies kind of the subject of our FEA simulation. So it defines the what and the where, we're going to solve our equations. And so practically, when we talk about the domain, we're basically talking about the geometry for your simulation. Oftentimes this takes the form of a CAD file, or this takes the form of a geometry that you might construct. And so for our first activity, that was our plate with the hole. And so when you think of the geometry, there's actually two parts of the geometry that are important to know. So let me go ahead and draw kind of a figure here just so you can see. Okay. All right, so here's kind of a very arbitrary geometry. And so I used to call this the arbitrary potato, but this is the one I drew here is like a weird looking potato. So we're not going to call it potato. We're going to call it our arbitrary geometry. So there's two parts of the geometry that are important to know. And so on the one hand, we have omega here, where omega is, we often call the interior of the geometry. And then we have delta omega here, or d omega. This is known as the boundary of the geometry. All right, so we differentiate between the interior and the boundary because oftentimes these two parts are going to follow different sets of rules. Okay, and so for instance, just at the very basic level, so on the interior of the domain, oftentimes we're directly solving our differential equation on there, but usually on the boundary conditions, we're solving different equations. So we'll have things like boundary conditions, which we'll talk about soon. But even if we're not solving boundary conditions there, then the equations that we solve have to be formulated differently because the boundary is a bit different. Okay, so oftentimes we differentiate between the interior and the boundary of the domain. All right, so at first, this may seem obvious, right? And so to run any kind of FEA, you need a geometry, like you need a CAD file, right? Like that's obvious. But I think a lot of times, you can save yourself a lot of work by really thinking about, what geometry is actually really important for me to analyze in this FEA. Okay, because it's very easy just to say, say you're working in a company, and you're the FEA specialist in the company, and so oftentimes you have somebody else that's producing the CAD model. Okay, so it's very easy to just take a CAD model from someone else, import it into ANSYS, and start working on the analysis. Okay, but oftentimes that's probably not the most efficient use of your time. Okay? So it's often useful to think about, what parts of the geometry do I really need to perform my FEA well? Well, this is something I go through a lot with my undergrads doing finite elements. So a lot of them are working. They're working on situations that are like this. And so we have a lot of undergrads working, and we have our undergraduate projects like Titan Rover, or Formula or Baja, right? So they have other people or other students that are producing the CAD files, right? And those CAD files are produced mostly so that students can actually construct whatever project that they're doing. Okay? But a lot of times those CAD files are kind of way too complicated to use for FEA, where the FEA should really just be focused on just kind of a small part of the geometry. And so when you're doing FEA, you have to ask yourself, what are the parts that are actually really interesting? Where are the stresses going to be concentrated? Where the deformation is going to be interesting? Okay, because what you don't want to happen is that you go through all the trouble of meshing a CAD file, you run the FEA, and most of your model is just not interesting at all. So you have basically zero stresses in most places. We have zero deformation. And most of the action is in kind of a small part. And so thinking about, what is actually the most appropriate, domain or most appropriate geometry is an important question to ask. And oftentimes could save you a lot of work as well. Okay.
Shouldn't be applied to assembly as a whole, but
I mean, sometimes you have to do a whole assembly. And so sometimes there are situations where, the entire assembly has like interesting stresses or interesting deformations that you have, or maybe the connections between the assemblies are hard to model otherwise with just the individual parts. And so every situation is a little bit different.
we can do assemblies.
You can do assemblies, yes. Yeah. And in fact, our next activity is going to use an assembly. Yeah. Mm-hmm. Next thing is the governing equations. And so, we've kind of talked about this a lot, so I'm not going to go into detail about this. Okay. So the governing equations are basically the differential equations that define how your part is going to behave physically. Okay? So if you're interested in the structural response, you have to solve the structural equations. If you're interested in the thermal behavior, you solve thermal equations. If you're interested in fluid behavior, you solve the fluid equations. Okay. So in ANSYS, we saw this interactivity. And so, before we even began, or the first thing that we did in ANSYS was we said, we're going to be solving a structural problem. Okay. So oftentimes when you're doing an FEA, you select the type of physics, or you select the physical behavior kind of near the very beginning of the analysis. Right. So obviously, choosing the right equation for your situation is something that's really important. Okay. But what we'll see throughout the semester is that the decisions that you make go beyond just choosing structural or just choosing thermal, because there's a lot of wrinkles that you can choose actually even in those decisions. Okay. And so, for example, for structural, maybe you have a situation where you can use a linear model. For example, linear versus non-material. And so a linear material, something like a metal, is going to behave very differently than like a non-linear, like plastic or something like that. Okay. Or even like a composite, right? And so the equations that you use to model linear deformation are different than non-linear. Okay. So we'll talk about that in the class at some point. Okay. Another example could be, let's say that you're doing fluids. I know a lot of fluid stuff because that is mostly my background. Okay. Whenever you do any kind of fluid simulation to CFD, there's a question of whether you have laminar or turbulent flow. Okay. So the equations for those are slightly different. They're all still Navier-Stokes, but they're different kind of versions on Navier-Stokes depending on what you're solving. Right? And even more complicated is that sometimes you want to solve for more than one equation at the same time. Okay. Oftentimes you're going to have physical systems where you're interested not just in the structural, not just in the thermal, not just in the fluid, but maybe multiple at the same time. Okay. So we call those situations multi-physics because you're basically solving multiple types of physics at the same time. And so one example that is pretty common is thermal and structural. Thermal kind of gets combined with a lot because a lot depends on thermal.
Dr. Chang, can you please repeat your last sentence?
Yeah, so thermal, what I was saying is that people combine thermal analysis with other types of analysis because a lot of material properties depend on temperature. And so structures is one like that as well. And so a lot of materials, like their density changes based on their temperature, things like their stiffness depends on temperature. And so if you have a situation where the temperature is going to be changing in your geometry, you're going to want to solve both structures.
I see. Thank you, sir.
Yep. And so one example that one of my students did last semester was he did a brake pad analysis. And so he had a situation where he's kind of in charge of designing the brake pad for his vehicle. And so when you're braking, basically what happens is all that kind of kinetic energy gets converted to thermal energy, right? And so the part, your wheels kind of heat up or the axle heats up, okay? And so what he was concerned about is that if he's braking too fast, that's going to exert too much thermal energy into his onto his brakes, And that might actually, make the material too soft. It might actually cause the material to kind of break. So, what he had to do was he had to do a combined thermal and structures to make sure that didn't, that his vehicle was not going to break down. Okay. Another common one is fluids and structures. And so this is called fluid structure interaction. And so this is pretty common too, because you have a fluid that's kind of interacting with a solid. Right? One of the most, I think, kind of the quintessential example for this is if you've ever seen a flag fluttering in the wind. Okay, so the flag is a solid material. It's very flexible though, but its behavior in fluttering depends very strongly on the wind currents. So that's very much a fluid and a structure problem. And you can't really simulate a flag fluttering without doing both fluids and solids at the same time. Okay. All right, so there's lots of examples of this. And sometimes you want to combine more than two. Sometimes you want to combine 3, 4, or 5 different physics. Okay, so, and so thinking about, what are all the physical processes that you want to simulate and making sure you account for all of those in the equations is an important step in FEA. Okay, and so the last part of a boundary value problem that we'll go over is the boundary conditions. And so we already did it. We already did a little of this in the first activity. Okay, and so the boundary conditions basically define. Physically, they define any kind of external effects that are acting on your geometry. And so physically, the terms that we'll use for boundary conditions most often are things like loads and constraints. Okay. So basically, if you have something external, so a lot of times, when you do an FEA, you have your CAD file, you have your geometry, but that CAD file is not going to be just by itself. It's going to be interacting with the outside world, kind of the external world, kind of in whatever situation it's in. Okay? And so any kind of external effects that are going to be affecting your geometry, affecting your domain, you often have to encapsulate those as boundary conditions. Okay? And so if you think back to our first ANSYS activity, we had 2. And so on the first boundary condition we had was a fixed constraint or fixed support, where we held kind of the left side of the plate fixed. And then our other boundary condition was a load, which was a force or a pressure that we applied on the other side. Okay. Sometimes in the literature, you might hear people talk about boundary condition as inputs. Okay. It seems like a strange name, right? But the reason for that is that, once, and this will become more clear as we do more ANSYS activities, that boundary conditions are actually the things that make your geometries do interesting things. Okay, and so, because without any boundary conditions or without any inputs, your geometry is just not going to do anything interesting, right? And so, for example, let's look at this chair. Okay? So I have this red chair. If you're on Zoom, you may not see it that well, but it's nothing exciting. It's just a chair, right? Right now, there are no inputs acting on it, and so it's not doing anything interesting. It's just sitting there. Okay. If I were to take that chair, if I were just kick it and kick it across the room, that would be something interesting because the chair would go flying across the room. Okay. And so what caused that interesting behavior? Well, I applied an external effect, which was my foot onto the chair, okay, which we can model as a boundary condition. So that would be essentially like a load. Okay, so we apply a load from my foot, we apply a force onto the chair, and then that's when it would do something interesting. Okay. Yep.
So in terms of like boundary conditions, for example, the applications of like thermodynamics. We make assumptions.
Yep.
In order to solve them.
Mhm.
Where do those assumptions come in answers?
Yeah, that's a great question. So the question is, oftentimes when we're solving, these kinds of systems, we have to make assumptions. And so they can come in a few different ways. And so, I would say you could probably make assumptions on kind of all three parts of this boundary line problem. And so on the one hand, you may make assumptions about the geometry. And so you may simplify the geometry to make the analysis a little bit easier, to make it easier to mesh. And so that's one way you can do it. Okay. Although I think probably the assumptions that you're thinking about in terms of, when you're solving the equations to make them easier to solve, a lot of those assumptions come into the governing equations. And so, let's say, let's take the brake example again, for instance, right? And so let's say that you're analyzing a brake pad for a car, right? And so we just talked about how it's very much a thermal and structural kind of system. But maybe you don't want to solve two systems at the same time because maybe it's going to be a little bit too expensive on your computer. And so maybe you solve just the structural part of the problem. And so that would be kind of a big assumption to make because you're kind of ignoring kind of a big part of the situation. But it would be a lot easier to solve. And so, I wouldn't say that's necessarily wrong, but you would have to justify that assumption, say that, because, I don't expect, maybe you're examining the brake pad of like a wheelchair or something, right? And so for that instance, you probably wouldn't expect that much thermal energy to come from a wheelchair that's braking. And so you could probably analyze that with just a structural equation. And so there's assumptions in terms of how much physics or how complicated the physics are that you can put into your FEA. And for the boundary conditions too, I think there's a lot of assumptions for this as well, because there's a lot of external effects where maybe it's really difficult to encapsulate it as just a single force or a single load, right? For instance, maybe you'll see in activity 3 actually that we're going to analyze a freeway sign, and one of the forces that we're going to exert on it is a wind force. And so wind, one way that you can model a wind load is you can apply just a uniform pressure throughout the entire sign. But that may not be exactly accurate. Maybe the wind's blowing faster on one side of the sign than the other. But you have to specify the boundary condition in some way. And so you make an assumption in terms of how you apply that force. Yeah. Mm-hmm. All right. Good. Any other questions on this? Sure. Mm-hmm.
So in terms of like the error approximation, does that increase or decrease when you combine two types of?
That's a great question. Yeah. And so generally speaking, when you kind of make that decision to include multiple physics, generally you expect the error to go down because you're doing a much more complicated situation. But there's a lot of other things there's a lot of other factors to account for as well. So if you're kind of really clumsy about it and you're not really doing the coupling very carefully, then it could actually increase the error as well. So you kind of have to be careful. So it makes the situation more complicated in that there's more ways that can go wrong. But if you do everything kind of correctly, then it should improve the accuracy of the situation.
Dr. Chan, can you repeat his question?
Yeah. So the question was, generally speaking, when you do multi-physics or when you kind of include kind of more stuff, is it expected that the error is going to go up or down, basically? And so Basically what I said is that, generally, if you're going to go through the trouble of adding additional physics or more complicated boundary conditions or any of that, generally the expectation is that the accuracy is going to go up or the error is going to go down. But there's also kind of more places where you can kind of mess up if you're not careful about it.
Thank you, sir.
Yep. Mhm. Okay, so the last thing I want to talk about today is a little bit about the matrices. Okay. And so we talked about at the beginning of class today that FEA basically is a method to take a differential equation and turn it into a matrix set of equations. Okay. Okay. And so result FEA. So again, it looks something like this. So we have a gigantic left-hand side matrix. Okay. We have our solution vector. Our right-hand side vector. Okay. May not have noticed this in the first activity because the first activity was very simple. And so, probably what you experienced is that after you click solve in ANSYS, then ANSYS gave your solution in a couple seconds. Okay. That's not necessarily going to be the case for a lot of our activities. And so a lot of times in our activities, you're going to hit solve, and then ANSYS is going to be computing, it's going to be thinking for a long time. Okay. And so usually, when ANSYS says that it's thinking, it's basically working on the system. It's trying to find a solution to this system of linear equations. Okay? And so even though I made the argument earlier that computers are really good at doing linear algebra, it can still take them some time if the system is a little bit too large. Okay. But the reason I'm kind of bringing this up is, I want to talk about kind of the structure of this linear system and kind of what you can expect to go in each of these parts. Okay? All right, so we'll go kind of, from left to right. And so this matrix right here, from a purely kind of linear algebra perspective, this is often called just the left-hand side matrix. So it's on literally the left-hand side of the equal sign. Okay. But in FEA, this has another name. So this is often called the global stiffness matrix, or just stiffness matrix for short. And what the global stiffness matrix is comprised of is that it's comprised of basically it's the way ANSYS or the way any FEA software computes the global stiffness matrix is that it takes into account basically the physical properties and the physical kind of behavior of the system. Okay. And so kind of relating this to kind of what we've been talking about today and what we will talk about in the future. And so when you think of things like the governing equations for the system, when you think of things like the material properties, those where that information kind of gets encoded is into the stiffness matrix. Okay. So that's the global stiffness matrix. All right, I'm gonna skip X for now because X, we'll come back to it in a bit. But this vector on the right, in purely linear algebra terms, this is often called the right-hand side vector, okay? But for FEA, it has kind of a special name because of what tends to go in here. And so this is often called the forcing vector, or global forcing vector. Sometimes it's even called the input vector, although I think that's a bit more uncommon. All right, so what goes in the forcing vector? So the reason it's called the forcing vector is that basically any kind of external effects that force your system to respond go into this vector. And so what's the part of the boundary value problem that contains these external effects? It's the boundary conditions, right? And so when we talk about boundary conditions, where that affects your global linear system is that it only does it on the right-hand side vector. Okay?
Dr. Tron,
Yep.
for matrix number A, the second phrase, it says computed based on the physical properties. That computed, is that what the FEA software is finding, or is that how we would get A?
Right. So basically, like we talked about, FEA is a transformation from the differential equations to this linear algebra. So the kind of, we're not going to dive really into it in this class. If you're interested, you can take a 541. That's where we really dive into it. But going from that differential equation to this matrix, it involves, what we call the finite element process. And so things like the material properties and the governing equations, FEA kind of works on that to compute this matrix here.
Thank you, sir. I guess what I'm asking in simple terms is, I'm looking at that matrix equation. There's two vectors and one matrix.
Yep.
So I guess what I'm asking is, what are the knowns? What are the knowns? So are X and B known, okay, so I'm confused. So is X and B known to the FEA user, and the finite element analysis software solves for A? Is that the way I'm getting?
No, so actually A and B are known, and X is
okay. Yeah, that's what I thought.
Yeah.
I was just making sure. Thank you, sir.
Yeah.
So A and B are known to the user before they even run the simulation, and the simulation solves for X, correct?
Right. So I would say that A and B are known to the software because oftentimes they're a little bit too big.
Yes.
The numbers are too small to really compute by hand. And so, if you're running an ANSYS simulation, probably you can extract the information somehow, but oftentimes the user doesn't really care what's inside these matrices. They only really care about.
Yeah, it's a computer.
Exactly. Yeah. So A and B are known by the computer when you hit solve, and then after it finishes solving, then it solves for X.
Perfect. Thank you, sir.
Yep. All right. So X here is the solution vector. So the solution vector contains basically the system response. So basically, how the system is going to respond to the boundary conditions. That information is encoded in the solution vector. So X is basically what the computer is solving for. So the reason I'm bringing this up, and so, like I said, you're never actually going to see this matrix. You're never actually going to see what these vectors look like. You're really only going to look at, first of all, what equations you're going to solve, and you're going to look at the result. Okay? But I bring this up because, when you kind of go through the finite element process, you select the equations that you're solving and you choose the boundary conditions. It's very easy to think about, all that just kind of goes into like the finite element, which is cauldron. And so you might think it just goes into a soup and then what you get is the solution. But, every decision that you make and every parameter that you set for FEA kind of goes to a specific part of the underlying math. Okay? And so I kind of want to just give you a little context in terms of, where everything goes and what it's actually trying to solve. Okay. All right. And so, of course, the next step in this process, once you assemble the system, it's kind of an ordeal to just assemble the system. The next step is to actually solve it. And so whenever you want to solve a large system of linear equations in a computer, you need specialized algorithms called linear solvers. Okay? So that's a term you might see come up. You'll see it in the settings of ANSYS as well, and we'll tinker with this a little bit later on this semester. That's kind of why I'm bringing it up. Okay? And so I think the fascinating thing about linear solvers, if you look at a matrix set of equations and you kind of think back to your linear algebra class, and you may have learned just kind of one way to solve these kind of systems. Okay? The big thing about linear solvers in a computer is that there are literally hundreds of different ways that you can accomplish this. And what's even more fascinating is that it's still, even today, it's still a very, very hot area of research. How can we write computer algorithms that can solve a linear algebra problem faster and better? Okay. And the reason for that is because for generally for a well-constructed FEA code, and you hit solve on your computer, and you're kind of waiting for the FEA to solve, it's going to spend 95% of the time during the linear solve. Okay? And despite decades and decades of research of like some of the top scientists in the world, we haven't really done much better than that. And so it's interesting, it's fascinating. Okay? And so we're not going to go into linear solver theory. That's a class all on its own. Maybe depending on who you talk to, maybe 3 or 4 different courses. Okay. But for you as a user of ANSYS, it's good to know kind of 2 different categories of linear solvers. Okay? And so the first category that we'll talk about is called the direct solver. And so a direct solver is basically a computer's version of how you would solve a linear problem. So a direct solver generally will find you an exact or a pretty much exact solution to the linear system. And so if you have a 100 by 100 system, then a direct solution method will give you the exact answer. Okay. The issue with direct is that it can be very costly for very, very large systems. And so I think for ANSYS student and ANSYS academic, which is the ones you're using, I think direct is the default setting. And the reason for that is because of the element limitations, because of of the limitations they put in the student version. Direct is often the best course of action. The simulations don't never get too expensive, and so solving it directly is often good. Okay. The other type of linear solver that you'll see in ANSYS is called iterative. Okay. And so an iterative solver, just kind of like its name, it doesn't seek to solve the solution completely. Okay. And so what an iterative solution does, and I don't want to call it guess and check, because that's kind of a little bit disrespectful to the algorithm itself. It's more of like a educated guess than refined. Okay. All right, so the benefit of iterative is that, this refining process, you can kind of cut it off whenever you want. And so you can control the cost of an iterative solver a lot better. But unless it's like a very, very simple problem, it's hard to get an exact solution to the linear system. So generally the accuracy is lower for an iterative solution. Even though the accuracy is lower for iteratives, actually sometimes that's desirable, because sometimes you'll reach situations and there's no way you can avoid it. And so depending on just the physical situations, you'll get a linear system that's called stiff. And so what that means is that because of how the system is responding, it's very difficult to solve for direct. And so by doing iterative, you introduce some errors into the system, but those errors actually end up being a good thing, because they actually kind of make the system a little bit more flexible and a little bit easier to solve than if you did direct. And so sometimes those errors are not necessarily a bad thing, but You know, those situations are not that common, but I've seen those kind of situations sometimes. Okay. All right, any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. So thank you guys for coming. On Wednesday, we'll do another lecture. So, you know, today is an off week. We have no answers today. And so Wednesday, I believe we'll start talking about some of the mechanics background. So, you know, some of the questions, Ivan, you asked at the beginning about the different kinds of stresses. We'll talk about that a little bit on Wednesday. Okay? So thank you, everybody. Hope you have a good evening, and I'll see you guys on Wednesday.
Thank you, Dr. Tron. Have a good night.
Thanks, you too.
Good night, Dr. Tran.
By the end of the semester, towards getting a certification for ANSYS?
That's a good question. That's been something I've been looking into for a while. I would argue that you're ready for it. But the course itself doesn't give a certification, but it's something I want to do in the future. I would say by the end of the course, you could definitely take a certification exam.
Because it has like structural and it has a CFD, so that fall under the structural.
Yeah, mostly the structural. Yeah, we're focusing mostly on structural. We'll do a little bit of thermal, a little bit of fluids, but mostly the structural. So I would say you're good to go. Yeah. Exactly.
So what I do is first
this one for the whole, just keep it the same. Yeah, same goal. Yeah.
2.5.
Exactly.
Also the nodes I want to ask, like, I just got the same nodes, like similar.
Oh yeah, I'm not worried about the algorithms. Yeah. Yeah.
You mentioned stiff.
Yeah. Yes.
I just didn't understand it.
Yeah, it was kind of just a little trivia at the end. So stiff linear system, what it basically means is that you have a linear system like this. Normally for a good kind of well-behaved system, you have a bunch of coefficients, right? Kind of all over the place. For a well-behaved system, all the coefficients are kind of roughly the same. So you'll have like maybe you'll have 2 orders of magnitude. Here, like 5,000. For a stiff system, you have a much higher range. And so instead of just whole variations, yes. And so like maybe your maximum is 5,000, but maybe your minimum is like 0.000205. This makes it very, very difficult. So imagine, just exactly. Because like you're doing things in a computer, and variables in a computer, they have a limited precision, and so you can only start with 16 digits. And so when you get into situations like this, you really start to kind of stretch that. That's why now the approach is really fast. Exactly. Thank you. Yeah. Did someone have a question on Zoom? I kind of heard something before I stopped here. Mariah, any final questions?
Oh, yes, sorry. I actually wanted to know if you were going to talk about any thermal or electrical simulations this semester.
We'll do a little bit of thermal later on in the semester, but electrical, no.
Okay, I see. Interesting. Okay, good to know. Thank you.
Yep.